And this one is 3.23 part C. So here we have a slanted beam and we need to figure out the shear force and bending moment diagram using singularity function. So first thing first, we will look at only the transverse forces on this so that we can calculate the shear force and bending moment. So for that purpose, I can take this force and divide it into two components. So the component that we transverse through this beam, which is this one right here, will be W0 cos 30. Okay, so when I draw this force vertically downwards on this beam, I can use W0 cos 30 and let's name this as W1 equals to W0 cos 30. In terms of reactions, we are going to get reactions at this point here and at this point here. So here we'll have R1 and somewhere here we'll have R2, and these distances are 2L over 3 and L over 3. So this uniform load, we can replace this by a point load, and the value of that point load is going to be, and the total length is L, W0 cos 30, so we can write it as L times W1. So we can find out the value of these reactions by doing the moment balance. If I do moment balance about this point, I will get R2 times 2L over 3 equals to L times W1, as will be acting at right center of this beam. So this distance from here to here is going to be L by 2. From this you can calculate your R2 is equals to W1 3 divided by 4 times L. And similarly, if I do the fourth balance or take the moment about 0.2, I can get the value of R1, which is W1 L divided by 4. So these are the reactions. So in this beam we have point load and we have UDL. So for point load we are going to use x minus a minus 1, and for UDL we are going to use x minus a 0. For integration, your first integration of x minus a will give you x minus a 0, and one more integration will give us x minus a to the power 1. And for this one, your first integration will give you x minus a 1, and second integration will give you x minus a 2 divided by 2. So this will be used for your shear force calculation and this will be used for your moment calculation. So let's write the intensity function for this. From this side we'll start with R1. So R1 value is right here, so we can use W1 L divided by 4. It's a point force acting at 0, so we are going to write it as x minus 0 minus 1. And then we have this distributed force. Now distributed force is starting at 0 and ideally it is going up to infinity because we don't have beam after x goes to L, so we don't bother really what's happening after L. So we can write this as minus W1 because it is acting downwards, starting at x equals to 0, so that's why x minus 0, and it's a point load, so it becomes 0. And then we have this R2, so we can write this also, it's going upwards, so plus 3 W1 L divided by 4. It is acting at a distance of 2L over 3, so x minus 2L over 3. It's a point load, that's why it becomes minus 1. So this is how your intensity function is. So from here to your shear force, we can integrate this with a negative sign. So that's how we get your shear force. We flip the sign, so minus W1 L divided by 4. Integration will increase the power, so minus 1 becomes 0, plus W1 x minus 0, integration makes it 1, minus 3 W1 L divided by 4, and this integration here will make this as 0. Now from here to here, for a bending moment, we can again integrate this with a negative sign. So we get your mbx, flip the sign, so W1 L divided by 4, integration of 0 will give you 1 here, plus or minus here because of sign flipping, x minus 0, integration gives you square divided by 2, flip the sign again, so W1 L divided by 4 and x minus 2L over 3, this integration gives you 1. So now looking at the geometry, it has two sections here, one is up to 2L over 3 and the next one is x greater than 2L over 3 here, right? So we can divide this into two segments. Your first segment is segment number 1 for x less than equals to 2L over 3, and then we have your segment number 2, which is x greater than or equals to 2l over 3. So looking at your singularity functions there, when we have x less than 2l over 3, your x minus 0 will give you a positive, but x minus 2l over 3 will give you a negative. So we will not consider it on this side. On this side, both x minus 0 and x minus 2l over 3, both of them are going to give you a positive number. So we are going to consider both of them there. Let's evaluate your v1 value based on this. So only functions with x minus 0 will be considered. So these two will be considered there. The first one gives minus w1 l divided by 4. X minus 0 to the power 0 gives you 1. So we don't have anything here. The next one is plus w1. X minus 0 to the power 1 will give you x. So that's how your v1 is. Now in your mb1, we'll evaluate this one and we'll evaluate this one right here. So first one gives you w1 l divided by 4. X minus 0 to the power 1 gives you x. Second term here, w1 x minus 0 square divided by 2 will give you w1 x square divided by 2 here. That's the value of your v1. Now when we come for your v2 calculation in segment 1, we are going to consider this as well as this. But since we have calculated already these two values, we can write v1 plus the last term, and the last term in this case is minus 3w1 over 4 here, and x minus 2l by 3 to the power 0 will give you 1. So we can simplify this. So we have minus w1 l over 4 coming from here, minus 3 w1 l coming from here. So this gives us w1 can be taken common, x minus l. Similarly for your mb2 calculation, we are going to have mb1 plus this last term here. The last term is going to give us 3 times w1 l divided by 4, and this x minus 2l by 3 to the power 1 will be x minus 2l by 3. So which I simplify and I can get w1 lx, which is combining this term and this term together, and then we'll have minus w1 over 2 times x square plus l square. So now we have got v1 here, v2 here, mb1 here, and mb2 here. So we can plot these. So let's draw one axis for this. So this is the axis system, and I have simplified the value of v1 mb1, v2 and mb2, so that plotting is going to be easier. So there are two segments. One is x less than 2l over 3, and the second one is x greater than 2l over 3 here. So if you look at your v1, we are going to plot in segment 1. So this we can evaluate the value at x equals to 0 and x equals to 2l over 3. So when I check this value at x equals to 0, I get minus w1 l by 4. So maybe I'll have a negative value somewhere here. When I substitute x equals to 2l over 3 here, I will get a positive value, which is 5 over 12 w1 l on the positive side. So now I can connect these two with a straight line. So this is how the shear force is in this region, and from this equation you can see that this crossing point right here is at x equals to l by 4, and this crossing point is important because wherever your shear force is 0, your bending moment is going to get a maximum at that point. Next we can plot your v2. So if you check the value of this at 2 points, one is x equals to 2l over 3 and x equals to l. At l you can directly see that this value is going to be 0. At 2l by 3 it will be minus w1 l by 3. So minus w1 l by 3 is going to be somewhere here. So we can now connect them with a straight line, and this drop right here is coming because of the reaction force R2 that we have. So now I can shade this region. So this is how your shear force diagram looks. You can mark the important values. So this one is minus w1 l divided by 4, and this one right here is minus w1 l divided by 3. Now for the bending moment, we can look at this equation for segment 1. So for this we need two values. So one may be at x equals to 0, second one at x equals to 2l by 3, and third one is going to be your peak value. Now peak we can clearly see from the shear force will happen at x equals to l by 4. So these are the three values that we need to plot for this. So if you look at x equals to 0, you can see that this is going to be 0. So we'll start somewhere here. So this value here is going to be minus w1l square divided by 18, which is at 2l over 3. Now we look at the parabola. From the equation here, the power x square has a negative sign, so it needs to be a parabola opening downwards, and the peak is going to be somewhere here for this parabola, right at x equals to L by 4. So now we can draw a parabola connecting these 3 points. So we'll start like this, and then we can continue in this manner so that we reach this point. And this is where your bending moment is going to be 0. So looking at this equation, you can see that this is going to be at L by 2 right here. Now this value right here, we can get this by substituting L by 4 into this equation. So if I do that, I get this value as W1 L square divided by 32. So this is for your first segment. Now the second segment, we have to plot this equation right here. So you can see that this equation is going to give you two values, one at x equals to L, which is 0, and another value at x equals to 2 by 3, which will match this value exactly. Now this is also a parabola opening down, and from the slope you can see the shear force is 0 here. The peak is also going to be happening at this point. So with that information, you can draw a parabola that goes in this manner. So we can draw this shaded part here. So that's how your bending moment diagram looks for this peak. So we have marked all the important values. This one here, this one right here. These are the peaks, and this is where it's going to be 0.